The power delivered to the load is many times greater than the power that's drawn from the signal source. So this amplifier gets this DC power supply to do the operation. So these power sources, they supply not only the power that's ultimately resulting into the amplification or the amplified signal, but also those powers that may get dissipated in the process. So this figure shows that there are two DC sources, one positive on the uh, we call VCC, and one negative, what we call VEE. The amplifier has two terminals, what we call V plus and V minus, which basically the plus one is connected to the positive side of a DC source whose voltage is VCC, and the negative is connected to the negative side, what we call as VEE. Now, the current drawn from the positive supply is denoted as ICC, and the current that comes from VEE is called IEE. So the power that's delivered to the source is then addition of a number of things that are coming together, and we sum them up together as the power. The DC power is then sum of two powers, which is power from the positive source and the power from negative source. So these two come together. This is just the bullet point, it's not negative. It's supposed to be just the bullet point. Now if there is power loss and power dissipation, we have to go back to the law of conservation of energy, which means that the powers that are coming in and the powers that are going out, they are equal. So the power drawn from the signal source and the power that's delivered to the load, we have added powers to that, which is the power supply and the power that's dissipated as heat. So you bring this all together, we get this equation which takes care of all the different parts that would be there for the system. Now, when there is input and there is output and there are other powers which are losses, so we have to know what is the efficiency. So efficiency is then load divided by the input side. But many times our input is much smaller, so we can simplify that relationship to be just simply the load divided by the power supply, and that gives us the efficiency for an amplifier. The power efficiency is an important performance parameter for amplifiers that handle large amounts of power, and we call them those kind of power amplifiers as power amplifiers. So just like they're used in output amplifiers for stereo systems. Now, let's take a look at an example. Example 1.11. The statement says that there is an amplifier operating from a single 15 volt power supply, and it gives a 12 volt peak to peak, so it's a sine wave, and for our calculation we'll have to use the RMS value, which will be 12 volt peak to peak, which means positive and negative side both, and we have to then take only one side, and we have to take divided by square root of 2. So up to this point, if I have to then find out my load, that would be 6 to the divided by square root of 2, which is the voltage, and V square over R is for power. So R in this case is given as 1 kilo ohm. So kilo, when it comes to the top, it would become milli. So that would be the load power. The input is given, which is DC power, and which is voltage times current, and that's given as 15 times 8 milliamp, and that also gives us 102 milliwatts. Let me just correct this. Now, the question further says, what is the power dissipated in the amplifier? So we know the input is 102, but load is getting only 18 milliwatts. So the difference is what is being wasted. So if I were to find power dissipated, that would be the difference. 102 minus 18 would be 100 and, sorry, this is 120 and that's 102. The difference of these two powers. Let me correct that. This is 120, and hence we get. Now we have to find the efficiency, and efficiency would be the load divided by the input side, which is 18 by 120 times 100, and that comes out to be 15%. So we can take these numbers and find out exactly what is the power efficiency of an amplifier, because that's an important performance parameter for these systems. Now, when you have limited input of DC voltage, how much amplifier can amplify? Can it go infinite? There is a limit on how much would be the range of input and output voltages for an amplifier to follow the linear transfer characteristics. So that linear part is what we are interested, because if we go outside of that, the signal would get distorted. So for an amplifier which is operated from two power supplies, the output voltage cannot exceed a specified positive limit and cannot decrease below a specified negative limit. That transfer characteristic is what is shown here, with the positive and negative saturation levels denoted by L plus and L minus. So this is voltage on this side, and this is the voltage level on this side. So this cannot go beyond that. Now, the input waveform, there are two waveforms, 1 and 2, coming from there, and they are being transferred into waveforms on the output side. The voltage that's input and the voltage that we get on the outside, there is a fundamental limitation to that. And if I were to write, I can either write it in the form of output voltage or the input voltage. In both cases, it's the same, but you will have to write one in the form of the other. That saturation would result into signal not having more value than the DC voltage that's being used to power the amplifier. So this would be then limited by, on the input side, by two voltages. On the upper side, it's limited by L plus. On the lower side, it's limited by L minus. And this is, we are writing in the form of input voltage, but this can be written in the form of output voltage as well. This is nothing but we are getting this from output voltage is equal to the gain times the input voltage. that's just what we have written it like that. So L is the voltage, the minus negative cutoff, the positive cutoff. So we are just writing in that form. We could also write it in the form of output voltage like it's shown here at the bottom. So there is saturation level up to which point we can take it, and beyond that on either side there will be saturation and there will be no more signal will simply not go beyond that level. We want to apply these amplifier circuits as building block in system, so we need to characterize and model their terminal behavior. We will find some simple but effective ways how we can look at their transfer characteristics. So this is where we have to then look into what is happening on the with the gain, with the resistances, where is the input current coming, what is the effect of resistances. So let's get into that. What we are looking at is this is a basic fundamental circuit, what we call as a voltage amplifier. So with a gain factor of AV0. So this is the important thing, what we call as the gain. Now here what we have done is we have written an equivalent circuit, and we have put this box around, which is nothing but separating the outside world from the inside world. So outside this is the input, outside this is the output. And we can, when we know what's happening inside, we treat it like a black box. Going forward, when we work with op-amp in the lab, we basically look at the values that are given for an op-amp, where we are given the gain factor for that amplifier. We are given the input resistance, which gives us the idea that when it draws an input current from the signal source, that's where there is a voltage drop on the input side of the amplifier. And then there is output resistance, which is on the output side, that takes care of the change in the output voltage when the voltage is drawn, when the current is drawn to the load. We show in this picture that a model like this has a signal voltage Vs with its own resistance Rs, and it's connected to a load resistance. Now the non-zero output resistance causes some of this output voltage to appear across the output. So if we now use a voltage divider rule, what we get here is we can find out what is the output voltage that we are getting, and that's given here, which is this guy, and its part that is showing across this guy. So we are using these two as a voltage divider, and we are finding how much voltage is shown across this guy. So that's as simple as that. Now, in order to not lose gain in coupling the amplifier output to the load RL and R0 have to have a simple relationship where we want R0 to be much smaller than RL. That would mean that most of the voltage would then appear around the load and not get wasted inside the amplifier itself. So we, for a given load resistance, we design it in a way that R0 or our output is much smaller than the load resistance, right? But in some cases, load resistance varies over a certain range. So we want the gain or the output voltage to be as constant as possible. So we design R naught much smaller than the lowest value of RL. Right? So then an ideal voltage amplifier is one where there should not be any output resistance, where we want this guy to be just zero. That's the ideal situation. Right? So in that case, if we have this guy and we have RL infinite, your total gain would be then equal to the output gain from that amplifier circuit if R naught is zero. Right? So in this case, then the voltage gain of the unloaded amplifier or the open circuit voltage gain would be AV naught itself. All right. So now, what is the overall voltage gain of the system? That's a combination of input voltage and output voltage. Let's take a look at that. So we can write that as V naught over Vi. Now, if I plug in this value here, what we are left with is AV naught times RL over RL plus R output. So here was the case that I was talking about, that if this is negligible, then these two become equal. All right, so now what is the overall voltage gain then? That would be then written in the form of output voltage and input voltage. So that's the overall voltage gain for the whole amplifier circuit. Now we can model this amplifier as a function of the source, the gain of the open circuit gain of the amplifier, input resistance, source resistance, output resistance, and load resistance, all of them, by simple manipulation of these relationships. And what we get is, we get a dependence on input resistance and load resistance. So there may be some situations where we are interested in the overall gain from signal to the output instead of the input to the circuit to the output. But now we are looking at the overall gain which comes from the source itself, from now going from a system where we have open gain, open circuit voltage gain, which is this guy, when we say the RL is infinite. But then when we want to find the overall voltage gain, we have to introduce the voltage that appears outside the amplifier across the load resistance. So this is nothing but we are using the open circuit voltage gain and multiplying with the voltage divider part to it. But this gives us a relationship that shows dependence on input resistance and output resistance. So many times that's not the ideal what we want, and that would then create non-linearity in the system if there is change in the load. So overall voltage gain can be simplified if we assume R naught is much smaller than load resistance and input resistance is much smaller than the source resistance. So we are many times interested to make an amplifier with high input resistance or a low output resistance. So in that case, then what we work is we make cascaded case, or we use buffer amplifiers that can satisfy the conditions which would take us away from this ideal behavior, but we would still be able to achieve those special circumstances which would dictate us going away from this ideal behavior. Let's take a look at an example. 1.12, which is a sensor producing a voltage of 1 volt RMS with a source resistance of 1 mega ohm is available to drive a 10 ohm load. So we can straight away see that we need to find out the voltage drop across the output, right? And that we can do straightforward way where we can do the voltage divider thing, where we say, okay, V naught is equal to 1 times we have 10 divided by 10 raised to power 6 plus 10, right? So this 1 volt is showing up across these two, and that can give us the output voltage that we get. So in this case, it comes out to be 10 microvolts. Just playing with the units. Now it continues. What voltage and power levels result at the load? So from load also we'll find out P equals V square R. So V naught square over RL in this case. So PL equals V naught square. So V naught again now is 10 to the power minus 6. That was the voltage that's coming up at the output terminals, divided by load resistance, which is 10. So this is V square over R. So we put a square. So the power at the load is then, with all manipulations, 10 raised to power minus 11 watts. Now it says if there is a buffer amplifier, unity gain, with 1 mega ohm input resistance and 10 ohm output resistance between source and load. So now what we have to do is we have to go and take the open circuit voltage gain and multiply it with the voltage divider at the output. So that would be then V naught equals 1 volt times how much of that is showing on the input, which is Ri over Rs, times the open circuit gain times how much is it showing on the output across RL. So they would then, we plug in the values, we have all of those things. Ri and Rs are 1, both are 1 and 1. We know AV naught, now it's given as unity gain. We are given load resistance, output resistance, all as 10. So what we get is the output voltage is 0.25 volts. And now we find out the power. In this case, now we use this guy as V square divided by load, which is now 10. So let me do it here on the next screen. So it would be 0.25 to the power 2 squared divided by 10. So this comes out to be 6.25 milliwatts. So now the question is voltage gain. So how much gain we get? So gain is that what is the output divided by the source voltage. So this comes out to be minus 12 dB. Similar way we can find power gain for this situation as well. All right, so let me clean so we can continue. So now looking at this example, so now we see that there may be requirements where we have to design an amplifier which have input conditions and output conditions that need to be met. So what we do is we design amplifier as a cascade of 2 or more stages. They are not identical. In fact, they are designed to serve specific purposes. So they give us overall amplification with large input resistance or maybe low output resistance. So then what we do is we design it in a way which would give us amplification plus give us low output resistance for whatever application we are doing. So in those cases, what we do is we cascade them together. So these are just examples of desirable characteristics. So what we do is we avoid losing voltage signal strength at the amplifier input. So we design it to have an input resistance much larger than the source resistance. It gives us small voltage gain, for example, but this is an example of that. So the first one is giving us very modest voltage gain, but what it is giving us is input resistance which is much larger than the source resistance. The second stage is doing the bulk of the voltage gain, and the third stage is just a buffer amplifier which is giving us a relatively large input resistance and output resistance which is much lower than RL. So to match the conditions that we wanted to take care for the ideal amplifiers. Now in this case we can again calculate the gains which come from different amplifiers, and we can find overall voltage gain and overall current gain and subsequently overall power gain from all these three cases. So that's an example which is given in the book. So I will not go through that, but there are few comments that I will make on that we take solution for each stage, and once we get the voltage gains for all three of those, we multiply them to get the total gain of the three stages in the cascade. In a similar way, from now to find the voltage gain source to the load, we take AV, which is the total gain of the three stages, and we multiply it with the factor that represents the loss of gain at the input. So which is then taking the input of 1 divided by the voltage of input of first one divided by the source voltage. So that gives us the voltage gain from source to the load all the way. So then we are taking the first one and just multiplying it with the overall gain. The current gain again is for the input and the output. So we do I0 over I1, which gives us the the current gain for the whole cascade. And the power gain is then where we have the PL and we have PI. So PL is VL I 0 and PI is V first voltage across the first one times the input current. So which is another way it can be the voltage gain times the current gain, and that gives us the overall power gain for the cascade. So now there are situations where we look at these stages and we have to design it in a way that we take care of the different needs, where we get the without stage 3, if you take it out, your calculation will become a little bit simplified. So instead of taking the gains of all three, then we will just take the stage 2, and that is what we will use in our calculations. All right, so there are other types of amplifiers as well, where we may just want to uh, amplify voltage, maybe want to amplify just the current. There may be application where uh, just the current is of interest and not the voltage. So there are different ways, and there are current amplifiers, transconductance amplifier, trans resistance amplifiers, which are used in different combinations, and each one have their own gain parameters and their own ideal situations that are required for them to get the maximum gain. And these are relationships that go with all of them for voltage amplifier, for current amplifier, for transconductance amplifier, and for trans resistance amplifier. Now, these all four types of these are basically the same. They can be interchangeable, and any one of those can be used when we are uh, modeling the amplifier, and they are connected through the open circuit voltage gain. So AV naught is what binds them together. So if you think about it, the short circuit gain AIS and the open circuit gain AV naught, they are related to each other. If we take these values and manipulate those, we can get to that relationship that's shown on this screen, where we can show that the open circuit gain is related to transconductance and trans resistor amplifications. Now, when we are working with the circuit, many times we have to determine input resistance and output resistance. So there are simple ways how it is done. We follow steps where we remove source voltage and we apply voltage to the output, and we measure the negative output current, and that gives us the output resistance from there. Now the current is, of course, it's flowing in the opposite direction, so we put a negative sign so we can get the resistance out of it. And if you look at the figure, this would be the circuit that we would get to get the input resistance, so to get the output resistance from this circuit. In similar way, the input resistance can be found from the input voltage and input current. There are some special cases where we have an amplifier which has operation where signal flow only in one direction from input to. So all these amplifiers that we have measured, they are unidirectional, going from input to the output. But there is, which in one way you can say that the input current and voltage are completely independent to the output. But this is not the case, because there is a coupling that happens in the signal at the which from the output it shows at the input. At this stage we'll not go. Once we get into the later stages, we'll see that we have to update our model to take care of that. Now, when we are dealing with DC circuits or DC, we are just worried about amplitudes. But when we are dealing with AC signals, another important factor or another important way how we characterize the amplifiers is in terms of their response to the input sine wave signals. So different frequencies that come in the input signal. So the signal that comes may have a bunch of frequencies, and the amplification on different frequencies may happen in a different way. So what it means is we would see the system that would amplify, and it may also result in shifting of angle, but not changing the frequency by itself. For some, more than the other, right? So it can result into the signal measured at the output would be the same frequency as the input, but it would definitely, for amplified signal, they would have more amplification, for more amplitude. But some of the signals may get attenuated, which means they will not show up, or if they show up, they are much less significant than they were at the input. So that's what we call as frequency response. What we do is we use this to get rid of some of the frequencies from a signal, and hence the idea of tuning a signal to respond to only certain frequency. And this is the reason many times we just analyze an amplifier on one frequency, but that's because we have already removed the other frequencies, or we are focused on a very small band of frequencies. And to measure the response of an amplifier, we can apply white noise. So we can apply a signal which has bunch of frequencies, and that can help us see that only the frequencies that we have designed it for, they are showing up on the output. And this is just figure to show that the output has different amplitude maybe, but it would have the same frequency. It may be shifted in phase, which is this angle phi or phi, which is showing the phase of the amplifier at this frequency omega. So that phi can be different for the other omegas, but that's a possibility. It may not. There may not be any phase shift. So power. So the amplifiers which respond to certain frequencies, we denote their transfer functions in a slightly different way, because now they have a frequency dependence. So the transfer function or amplifier transmission, we write it as T of omega. Now here we are talking about directly the magnitude gain from the output divided by input, but the gain is something which we would present as a positive number. It can be negative because of phase shift. So if it is positive on the input side and you have a phase shift, it's negative. So there may be a negative that's coming in, but we talk about the response in terms of positive numbers. And another thing that would be important for that transfer function would be the phase shift. So we write it with this angle sign and the omega at that frequency, how much is the shift. So what we get is we get a table or a graph of gain magnitude, which is the left side, versus frequency, and or maybe a graph of phase angle, which is on the right hand side, versus frequency, which means Then we can see that when we change frequency over a spectrum, we go from maybe, let's start from 10 hertz, we go 20, 100 kilohertz, 10, 20 kilohertz, and megahertz. So we sweep the frequency. How does the magnitude change? All right, we can take a look at that. Or we can see how does the phase change across that shift or the whole frequency spectrum that we are interested in. So we would then take that number and draw the behavior of a device, and that would give us what we call as bandwidth. Now here's something which shows up on the left hand side. So this is nothing but the response or the uh, magnitude of the transmission. And just like gain, what we are showing here is the transmission response, and that's also written in decibels. Now, what does it tell us is that when we are going over frequency range, some signals would be getting attenuated, and then there would be a range when over that frequency the response is flat, right? So we are getting equal gain over that range. So the band of frequencies over which the gain is almost constant to certain number of decibels, we call that as amplifier bandwidth. So that would then tell us this amplifier is going to be amplifying certain frequencies and not others. And this is an important parameter for a device, for an amplifier, where we can get rid of some frequencies and keep others. When I say get rid of some frequencies, that's an important part of our networks where we want to analyze or design amplifiers where we just want to focus on one or a small band of frequencies and not all of them. Now, so far, the circuits that we have seen, we were dealing with resistances. But now we are bringing in components into a circuit which what we call reactive components. So reactances are resistances, but they it is capacitor and inductor. So they have resistance, but they also have effect on effect on the frequency of the signal that is going through. So what we are now dealing is, we call them single time constant network, or the frequency response of an amplifier where we are using reactive components, and reactive components are inductor L and capacitor C. So when we do that, we will do the similar usual analysis, but now we will be introducing inductances and capacitances represented by the reactances. So an inductance L has a reactance or impedance that's written as j omega L. So if I were to, for L, for an inductor, I would use its reactance as j omega L, and for a capacitor, I would use it as 1 over j omega C. So which means now the reactance is the resistance, but it's coming from these components which have a frequency response. So we call them reactance. So they have a dependence on the frequency. And having them in a circuit brings up another concept which is called time constant. So that's the length of time required for a network transient to settle from any step change. And it's L over R in case of an inductive reactance, and it is RC in case of a capacitive reactance. Now, with this idea, we can create two kind of filters: low pass filter with a capacitance, and a resistance shown on the left hand side, and a high pass filter which is where capacitor and resistance are shown in the way on the right hand side. These circuits would result into either letting a frequency above a cutoff to pass, which would be high pass filter, or if frequencies to pass below a certain cutoff, which would be the low pass filter. Now, in this case, when we are finding the transfer function T omega, this would be now a complex function whose magnitude T omega, like before, gives the magnitude of transmission or the magnitude response of the amplifier, but the phase gives the phase response of the amplifier. So in a similar way like before, where we were looking at the output as the voltage divider, and we are looking between RL and RI, now we are looking at the reactances from those components, so j omega C or j omega L. So here, low pass, high pass, we are RC circuits are what are used for that. So we are using then their combinations of their so the combination of which part is shown on the across the load in both cases would result into what gain do we get for both cases. So many of these would give us very specific cutoff depending on what are the values that are chosen for those specific circuits, and their transfer functions, magnitude responses, and their transmissions at different values are given by this table. This table helps us calculate directly from the given values for the resistance and reactance, and that can help us do the analysis in a much faster way for the different cases of low pass or high pass filters. A simple way to graphically present the gain and phase shift against frequencies is done by what we call Bode plots. So Bode plots they tell us the gain and phase representation, and these are very important in the design and analysis of the frequency dependent behaviors of systems where we are dealing with the magnitude and phase response of STC networks, whether they are of low pass type or high pass type. So we define the cutoff of the bandwidth also by using the 3 dB points where the signal amplification reduces by 3 dB, and we take that as cutoff for the that STC network or that circuit. So now, given the amplifiers which behave based on their frequency or the frequency that is coming in, we use internal capacitances in devices, and we use coupling capacitors, which give us many different applications where we want to amplify to maintain its gain at low frequencies all the way to DC maybe, or maybe we have a signal which is almost constant, so or if there is any fluctuation we want to get rid of, like maybe temperature based sensor output changes. So we use these capacitances or capacitors to many times couple different stages as well. So, but we have to know what is the value that we need and what kind of relationship we want at the from one stage to the other stage.